random number generator you now have.
Okay. Hi, everyone. Today I'm going to talk about random number generators, and this is a joint work with John Kelsey and Kerry McKay. They're sitting there, and yeah, hi, John. And so we are part of the crypto technology group at NIST, and we're working. This is a part of the work we do at NIST. Okay, this is my outline. So I'm going to talk about random numbers, and then why they are important, and how we check the quality of those random numbers, and we check its entropy. And this is part of the work we do. It's about the special publication 890 series, and this. In 890b includes a couple of entropy estimators, and now we are trying to study more on them, and we want to add new estimators to this document. And today I'm going to present you these new estimators, which are based on some of the machine learning techniques. And I'm going to present some experimental results and conclude the talk. Okay, so you all know generating secure random numbers is the crucial part of pretty much all of the crypto protocols, and they are also used in cryptographic key generation, IV initialization vector generation, or if you need some random padding or some other random values in protocols like TLS, you really need random numbers. So, as I said before, yes, the security of all these protocols relies on the security of these random numbers. And we sometimes believe that these operating systems, the operating systems that we use today, are able to generate random numbers that are secure. We can trust them. But in 2012, Henninger and her colleagues just presented a paper, and then they showed that this assumption is not always correct. So they made the largest network survey of TLS and SSH servers. They collected a lot of certificates from TLS hosts and SSH hosts, and then they started analyzing these certificates that they collected. This collection was done in like a couple of days, and then after studying these certificates, they had some interesting results, and they see that some of the public keys were repeated, which was unexpected, and then they were also able to recover some of the private keys for these certificate RSA keys and the DSA keys, which was really surprising for everyone. And then they tried to find out why did this happen, and they have found a couple of reasons. Sometimes people using the default manufactured keys, but the main reason now we're interested in here is the low entropy using key generation. So they realize that this happens sometimes in the routers where they do not have, these devices do not have access to a lot of entropy sources. So they started generating the same keys over and over again. Okay, so we say that entropy is important, but what is it? So entropy has different definitions in different fields. So it's originally defined in thermodynamics, but now we're considering information theory definition, of course. And then this definition tells us that entropy is the amount of information that contained in the message. So a message can be an event or a sample from a distribution. So entropy characterizes the uncertainty about the source of the information to us. So even in information theory, there are different definitions for entropy, which the first one was given by Shannon in 1948. And there were other definitions like mean entropy, Raynier entropy, and actually many others too. Let me talk a little bit about Shannon entropy, which probably you're more familiar with. So it's related to the performance of the compression algorithm. So let's suppose we have mathematically, let's suppose we have a probabilistic process which takes n different values from x1 to xn. And each of these happen with probability p1 to pn. And then the Shannon entropy is defined as the negative logarithm of the with the summation probability times the logarithm of the probability. So this is how Shannon entropy is defined. So it really, as you can see from the formula, it really doesn't depend on the values of xi's. It only depends on the probability distribution of xi. And here we use the logarithm base 2, but actually the base really doesn't matter. You can use any base here, and you only need to multiply with a constant if you need to change the base. So let me give you a classical example where we flip a coin. So we have two possible outcomes, head or tail. So assuming the coin is fair, the probability of obtaining a head is one half, and tail is 1/2 as well. So in this situation, the Shannon entropy of this process is, if we plug in the values, it's obtained as 1. And so after we toss a coin, we know we get 1 bit of information. And if we assume that flipping these coins are independent, so if we flip the coin k many times, we get k bit of information. Okay, so let's assume we have a biased coin where we have probability of obtaining a head is a lot higher than probability of obtaining a tail. Then in this case, the entropy and actually the uncertainty about the event reduces, then the entropy reduces. For example, when the probability of obtaining a head is around 75%, our Shannon entropy becomes 0.8. And if we have a coin where both sides are head, then when we flip this coin, we get no information at all, and the entropy for this coin is 0. So Shannon entropy gets its maximum value when all the events have equally likely, all the probabilities are same. Okay. So in crypto, we're not really worried about the performance of the compression algorithms. Now we're interested in the predictability of our keys. So we don't want our keys to be predictable. So let's assume we have a block cipher and which takes 128-bit keys. And we assume that we select our key randomly from the whole set of possible keys, and then we assume that if the block cipher is secure, the best chance the attacker can do is try 2 to the 128 many keys to break our cipher. But this will not be true when the keys are not generated randomly. So let's assume the case we have with 1/2 probability, our key is all 0, and with 1/2 probability, the rest of the keys are selected with equally likely. Then if we plug in the values for Shannon entropy, we see that the Shannon entropy is going to give us a value like 65 bits. So this, we might think that, okay, 65-bit, then the attacker is going to have needs to try like 2 to the 64 many times, which is not correct, because the attacker in this situation is going to guess the correct key with 1/2 probability even in his first trial. So Shannon entropy is not really suitable for what we do, what we care about, which is unpredictability of the key. So that's why we use mean entropy to calculate, to check the entropy of our keys. Okay, so what is mean entropy? Again, mathematically, we have a probabilistic process that takes values from x1 to xn with some probabilities. Now we only care about the maximum probability, the event that happens with maximum probability. So it is the minus logarithm of the pi value, which is the maximum among all values. And Shannon mean entropy is always bounded by the Shannon entropy by definition. So, and when we look at the previous example where we have equally likely keys versus one key that happens half of the time, so now we calculate the mean entropy. For the first case, it is equal to the Shannon's entropy, which is 128-bit. But when we look at the second part, the mean entropy is going to be just 1. So it will just give us more information about the unpredictability of the keys. Okay. So now let me talk a little bit about the NIST 890 series. It's about cryptographic random number generation, and this is the document. This document has 3 parts: 90A, 90B, and 90C. 90A is related to deterministic random number generators, which are basically pseudorandom number generators. And then if you seed them with a secure random value, they are suitable for generating cryptographic random values, of course up to a value depending on the length of the seed and the entropy of the seed. And they can be used, they have good statistical properties, and they are safe to use. Now we have 90B, where we think about entropy sources. The entropy source, these are the sources that these output seeds for the deterministic random number generators. And then we have the last part, 90C, which kind of combines it tells you how to construct the random number generators with the deterministic part and the entropy source part. So it's just kind of a glue between 90A and 90B. Okay, this talk is actually about a part of 90B. So, okay. 90B document defines an entropy source model. It's given as in this figure. So we first have the noise source. It extracts some randomness from a physical phenomena. It could be like a radioactive event. It could be a ring oscillator. It just can, or from your mouse movements. So this extracts randomness. And we also have a health test in our model. In the health test, we know that these noise sources are usually very fragile and can be affected by the change in the temperature or humidity. That's why we want to continuously check how the noise source is doing. It might be stuck in a value. It might be giving the same output over and over again. So we want to make sure that the noise source is working correctly. And the last part is the conditioning function, which is an optional deterministic part, which is used to actually just to reduce the bias of the outputs that we obtain from the noise source. So to increase the statistical quality of the output. Okay, so here we have a noise source that outputs some values, and then given this long output, we want to estimate the entropy. And here we know that the output of the distribution is unknown to us. As I said before, the entropy depends on the distribution of the output, probability distribution. So we want to detect the probability distribution from the output, but we have to keep in mind that it's not always, the samples may not be independent from each other. And also the distribution of the samples from when we start the device might be a lot different from the distribution of the samples when we run the device like 2 days. So this is a thing that we have to keep in mind. Okay, if we overestimate the entropy, we might, this has some security problems. So if we think that our key has 128-bit of entropy, but it has only 40-bit of entropy, it's a lot more predictable to the attacker that than you think. And underestimating entropy is a problem too, because this is related to performance. If you, it will take a lot longer to generate a 128-bit key if you underestimate your entropy. Okay, and also your random number generator might block some of the applications because it's not fast enough to produce keys, and then the implementers might say that, okay, I'm just using pseudorandom number generator instead of a random number generator that includes no entropy at all. So this is also a security problem too. In 90B, entropy estimation is done by by accredited crypto security labs. So NIST just published this document where it tells you how to generate, how to estimate entropy, but this is done by the labs. So there are a couple of challenges here too. So the estimation process cannot be really too complex, and because there are some time and cost considerations. And then any two of the validations labs must give the same result to the must make the same as entropy assessment, and also. So we want this entropy estimation as independent as possible from the internal structure of the noise source. Well, we don't want the process to require a lot of expert knowledge either. Okay, so for samples that we do not assume to be independent and identically distributed, 90B, the latest draft of 90B, which is out since August 2012, has 5 estimators, entropy estimator. They are designed by Haggerty and Draper. They work for NSA. So we have 5 estimators. One of them is frequency estimate. It just checks the frequency of the most common value, most common sample. The second estimator is the Markov estimate. It just models the system as a Markov model, one depth Markov model. And the other one is a collision estimate, which is based on the average time a collision occurs, which means a sample value is repeated. And partial collection is based on the number of distinct sample values that we observed in a time period. And then we also have the compression estimate. And when we have these 5 different estimates that models the entropy source using different assumptions, of course we get different entropy estimates. And then we get the minimum of, we want to be as conservative as possible, and then we get the minimum of all these values, and this is our entropy assessment. Okay, let me a little bit talk more about the entropy estimate. Frequency estimate. So in the first one, we just get the output and then calculate find the most likely value and check its probability, and then we calculate an error value based on our confidence level and number of observations that we have. Then our entropy estimate is simply the negative logarithm of the P max value that we see and plus an error value. In the second estimate, we model this source as a first depth Markov process. So it is simply assumes that the samples are not independent. The current sample depends on the coming sample depends on the current sample value, and it's independent of the previous values that we received so far. So here, if we have the samples A, B, and C, we construct a transition matrix where we have, okay, what is the probability of getting the next sample as B, given that our current sample is, let's say, C. So we construct this transition matrix, and then using this transition matrix, we try to estimate the most probable samples that we're going to obtain. And of course, this is good for catching some first-order dependencies between samples. So we have 3 more estimators: collision, partial collection, and compression. They are all based on the same idea that we first, of course, we get the output from the noise source, and then we construct some test statistics from. We convert this noise source to a test statistics, and then calculate the average of this. And then we're trying to fit this statistic to a near uniform distribution. In near uniform distribution, the samples, all of the sample values takes the same probability, has same probability except one sample value. Here, sample A has probability B, and the rest of the sample values has Q, probability Q. Here, P is assumed to be larger than Q, of course. And then we're trying to minimize entropy, and we're trying to find the p-value that using the calculated test statistics. We have a model, and then we are trying to minimize the entropy value based on this model. In the collision estimate, the test statistics is based on the average time until the first collision happens. So let's assume we have the samples A, B, B. So we see that B is repeated, so our first test statistics is 3. And then we forget about these first 3 samples and then start from the beginning. Now we have CA, BA. Then we see that A is repeated after 4 samples, so now our next statistics is 4. And then we just convert this samples to the test statistics and get the average one. So it is good for catching the cases where the most likely value changes over time, so which may not be which we will not be able to catch with the previous test frequency estimator. In the partial collection estimate, we divide our samples into non-overlapping blocks, and the non-overlapping blocks has fixed size. Here in this example, we have we selected the length of the blocks as 4. Within 4 blocks, how many distinct values we observe? So in the first block, we have A, B, B, C, and we have 3 different samples. And we calculate these for the rest of the samples too. And we see that the entropy estimation is low if the number of distinct values is low. And if we have more values, then our entropy estimation is going to be higher. And the last test is about the compression estimate. It's based on the average compression using universal Maurer test statistics. It has 2 phases, like one training phase and a testing phase. So in the training phase, you just check the indexes of each sample value, and in the testing, we want to see how frequent each value is. So our first sample value is A here, and then we see where A appeared previously. So we see that A was the previous value, so our test statistic is 1 here. So, and our next sample value is B, which appeared 4 samples before. Now our second test statistics is 4. And going on like this, C appears again 4 times before, 4 samples before. Okay. So that's how we calculate the test statistics, and then we take the average and try to fit it in a near uniform distribution. Okay, so what are the drawbacks of these 90B tests? So we made we just generated a lot of simulated data and tried to find out how these estimators did. So in some of the cases, we see that when the model is incorrect, the estimates are sometimes significantly lower than the actual estimate. So since we simulated these data, we know the correct entropy estimates that we are that we want to estimate the correct entropy value. So we are able to see how good these tests are doing. So usually, and in some of the cases, the estimators did not work very well. For example, the multi-Markov model, the estimates that we get from the 90B was higher than the what the real entropy was compared to the real entropy. So this is a more serious problem too. And there might be cases where the entropy doesn't work when there are more dependencies between sample values. So that's why we want to have an alternative approach for the next 90B draft. So now, since we're interested in how hard it is to predict our cryptographic keys, we are thinking about, okay, so we observe these samples, A, B, C, BA, BA, BA. How easy to predict the next sample value? So we wanted to estimate entropy based on such predictors. So we know that if we have a good predictor, it will give us an accurate entropy estimate, and we see that if we have a bad predictor that doesn't fit to our model, it will be an overestimate. But if you look at the many different predictors and get the minimum one, we hope to get close to an actual value. So how do we do? So we have predictors. How do we estimate entropy based on the predictors? So we try to calculate a p-values, which is the probability of correct predictions. We have two ways to do this. The first one is we look at the samples, we look at the predictions, we know which one are correct. After we observe the next value, we know if our prediction is correct or not. So we can just calculate the number of predictions we've done over number of correct predictions we have done over number of total number of predictions. So this gives us a fraction of proportion of correct predictions. And there's another measure that we can look. So let's assume our device, after running for some time, falls into a state where it's really easy to predict the next output. So we want to catch those situations too, because maybe the device might be generating our cryptographic random number, cryptographic key during that phase. So we want to catch the phases of the device where it is really predictable. So then we check the correct predictions and the length of the longest run of predictions, and then we can also estimate a probability value from this length of the longest run. So we get the minimum value of these two predictions to estimate the entropy. Okay, so predicting the next sample value can be viewed as a classification problem too. Previous observations may be mapped to data tuples, and the output may be mapped to a label. And a prediction can be considered as a classifier. And here we do not have a separate training and testing phase, because when we get the correct value, so we made a prediction. When we get the correct value, we update we have the time to update our model too. Okay, the good thing is about predictions that they do not assume that the samples are independent. We don't have to do this assumption. And another assumption that we do not have to do is that the underlying process is stationary. So this is one of the advantages of using predictors. And now I'm going to describe three predictors that we have, which are most common value: multi-Markov model with counting, and lag predictor. Okay, most common in window predictor, it just basically stores a window of last W samples and calculates the most common value based on that, and then it predicts this value as for the next upcoming sample value, and W is selected as 64 in our experiment. And it's good for sources when some of the values appear more frequently than the other, but the probability distribution changes over time. The second one is the multi-Markov model with counting. It keeps track of multiple Markov models simultaneously with different depths. So in our experiments, we use depths from 1 to 16, and then we kept a scoreboard for each model to see which model behaves better for that time, and then try to make our prediction based on these scoreboards. Okay, the last predictor is the lag predictor. It is also very simple. It just it just predicts the upcoming value of the next sample value is predicted by last ith sample value, and it keeps track of multiple lags simultaneously. So here we used up to 128 previous values, and then we keep a scoreboard for each model, and then if one of the models starts to predict more correctly, then we use that model, and then after every prediction we update our model. So let me go over our experimental results now. Okay, so we use a lot of simulated sources with known probability distribution. So we selected some probability distribution. Because we know the probability distribution, we know the entropy of these sources, and then we check the accuracy of our entropy estimations based using our predictions. And of course, we need a variety of sources to see the effect of different behavior. And we created data sets using 1 million samples for each data set. And then target entropy was given as input while we generate these data sets. Okay, we use 5 different probability distribution. The first one was the uniform distribution, where all the samples are equally likely. And we use the near uniform probability distribution, where all the samples have equal probability except one. The one that has one of them has a lot higher probability than the others. And we also have the Markov model. It is we assume that the samples have some dependencies between each other, and then we construct a transition matrix and generated our sample values based on these transition matrix. And we also generated some values from a normal distribution, but we use a discrete approximation for this. And lastly, we use time-varying normal distribution. So at each point, every sample comes from a normal distribution, but the mean of the distribution changes over time and follows a sine wave over time. So it just increases and decreases. Okay, so these are our sources that we used. Let's look at some of the accuracy of some of the estimators here. So the red lines gives you the actual entropy. The blue line here gives you the most common window predictor, and the green line gives you the estimator, the 90B estimate. As you can see, 90B estimators are a little bit lower estimates the entropy, especially when you.
On the screen, it's showing the 90B estimates are showing as white. On the projectors,
should be green, but yeah, at least it's green here. So the white line is the 90B line. Okay, when we check the, again from uniform source, when we look at the multi-MMC predictor, which is the multi-Markov model with counting, we see that again 90B, which might be the white line there, lower estimates the entropy, but a multi-MMC also has some lower estimates. And when we look at the lag predictor for the uniform distribution, it is closer to the actual entropy. So as a summary for uniform source, we see that the three predictors followed the correct entropy line more accurately than the 90B estimates. 90B estimates were lower, they are more conservative, but there are some performance penalty issues involved with that too. So we want to estimate entropy as accurate as possible. Here. Okay, so I'm going to show you a couple of more graphs. So when we have the near uniform source graph, we see that multi-MMC performed best when, and other gives many overestimates. When we see that other predictors, they're not shown here, but gave us a lot of overestimates, which were not good to estimate the entropy. And for the Markov source, again, multi-MMC performed best of the three predictors. And we have some higher estimates for 90B here. This is so small, I can't see my screen. And for the normal source, for the samples that are normally distributed, again, multi-MMC had a linear trend that is closest to the normal source. And then the others has some overestimates and upper estimates. But we can see that the 90B is significantly lower, gives a low underestimate for the entropy here. And this is same for time-varying normal source too. 90B again, 90B estimates are significantly lower than the actual entropy. Okay, if I make a summary of these results, there are a lot of graphs, but we see that 90B estimates that are currently in the standard can make approximately like 40% deviation, has changed difference in the compared to the actual entropy. But this is we see that for most common value for the most common value predictor, the estimation is around 20%, and then this is the lowest for the multi-MMC models compared to. So this brings us this shows a significant improvement compared to our current 90B estimates. As summary, 90B estimates are more conservative and usually provides us an underestimate for our simulated sources. And if the model is incorrect, it can be a significantly lower estimate, but at the same time, there are some situations that the current 90B tests are unable to catch, and then in those cases, we were able to show some of the cases where it gives us very significant upper estimates, higher overestimates too. And we see that estimators based on the predictors are more accurate, more closer to the actual entropy line, actual entropies. But one problem here that we always, in this study, we use some simulated sources, which are not actually the real sources, then that we don't know so it's important to keep in mind that these are simulated sources, not the real entropy sources, okay? And of course, we need to do more analysis using the real-world data. Okay, I think that's all. Yeah. Okay, or I can give you the mic. Not really. Okay.
Yeah, my question was, what are your thoughts on open sourcing hardware random number generators?
I don't have.
Okay, so I think it's a great idea. I think it's a really good idea for people to design these, design as many as you want, and have people look at them. I think there's a real benefit to having something like the Intel RNG, which is, it's sort of closed, but it's mass market and everybody has one. One problem with the sort of the open sourcing ones where somebody says, okay, here's how you build it, is that it's hard to get my mom to use a good entropy source then, because she's not going to be like breaking out the soldering iron, or even like running a program, downloading something from the internet and running it. Well, she does a lot of that, but not good things. So I think it's really cool. I think one nice thing about this is these tests that we're working on are generically useful. They're something we're providing for the validation labs to try to get them to do something, because right now the validation labs, as far as entropy estimation, they don't really have much of anything. They're doing kind of their own minimal tests to try to figure out that what they're being given is not complete crap, but they don't have very good tests. And we're hoping to kind of raise the bar with these. But these tests can be used just as easily by a developer. And in fact, I think one thing we're hoping for is that people will look at the standard, and when they're developing their entropy source, their noise source, they'll run some of these tests as a first cut to find out what's going on. So yeah, I think it's a really good idea. I'd love to see more people doing it.
Thanks, John. Okay.
So the draft 90B has been out for a little while now, and the tests in it, excuse me, way better than what we see in something like FIPS 140-2, in that they're testing, noise before you do the conditioning. And what you're showing here seems to be sort of significantly new testing that needs more validation. So how do you see that impacting the timescale for getting the full publication?
I get to answer that one? Okay. So the way I said, first of all, I want to make a distinction. What we're talking about here are for validation testing. This is not the continuous testing. The continuous health testing is a different thing. Okay. So for validation testing, the nice thing about these tests is because we're thinking in terms of adding some of these predictors and some of the other tests to the things we already had in 90B before. Maybe taking out a couple of the NSA tests that didn't perform very well. But the thing you're going to do is you're going to take the minimum of all those estimates. So if you have a predictor that doesn't perform very well, it doesn't really hurt you very much. It doesn't, it can only make things so much worse. Now, if you have a lot of tests that can give wild underestimates as well as wild overestimates, then you have a real cost to adding like 10, yeah, thanks, 5 minutes, yeah. To adding like 10 more tests, and some of them sometimes give 0 or something, because then you just ruin some sources. But as long as you have a lot of sources that are a lot of predictors that never give big underestimates, but sometimes are very accurate, you can just take the minimum of all those and you get a pretty good result. That answers. So as far as the timescale for 90B, we're trying to come out with a new draft of 90B early this year, and we're planning to put these predictors in it, right, along with some other stuff that we're doing, and then hopefully get some more feedback. We want to get this done. We want to get this stuff done this year. So.
How would lossless compression algorithms fare as an estimate for the entropy of a random number generator?
So we do this, actually. The current draft that's out there, that's been out there for a couple of years, uses BZ2, the Burroughs-Wheeler coding, as a lossless compression algorithm, as a sort of a sanity check. When we've done experiments with this, what we find is it's never the low estimate, okay? You're just trying to solve a different problem, right? So really, you're here with Burroughs-Wheeler coding, you're trying to figure out how to make general purpose like text and stuff shorter. And if you've ever studied Burroughs-Wheeler, it's hard to get your brain around at first, and then it sort of clicks in your brain and you see why it works. We also tried several other compression algorithms. At some point recently, Kerry ran a whole bunch of a big suite of different compression algorithms to test them all. And there are some that are a little better than Burroughs-Wheeler, than BZip, but none of them that make much of a difference. They're always overestimates. They're always big overestimates, and they're never the low estimate on anything that we run. Even if we just did the Burroughs-Wheeler coding and then looked at the length, and then we just did like the 90B tests or just the predictors or anything, the compression is always the biggest number. If that makes any sense. Do we have other questions? Oh, sorry. Do we have other questions?
Okay, thanks, John. Thanks for the questions. Okay.